You're listening to MedX, the Medical Extrusion Podcast. Presented by U.S. Extruders. Extrude with confidence. Custom extrusion equipment designed for you and your application.
Welcome back to the MedX Podcast. Today's discussion is focused on single-use deflectable endoscopes, and our guest is Alan Iranian, Director of Endoscopic Steerable Catheters at Biomerics. Flexible endoscopes are used to treat a broad range of gastrointestinal and pulmonary conditions minimally invasively. The big news in endoscopy is the transition from reusable endoscopes to single-use endoscopes. Reusable endoscopes are expensive and complex devices that require time-consuming and resource-intensive reprocessing after each procedure, which increases the risk of contamination and infection. This has created an opportunity for developing single-use endoscope platforms. The FDA is recommending transitioning to single-use platforms that eliminate the need for reprocessing. Last year, Medicare and Medicaid services approved and are incentivizing the use of single-use duodenoscopes. As a result, the disposable endoscope market is expected to grow 15 to 20% over the next 5 years. Alan, welcome to the MedX Podcast.
Hi, Steve, and thanks for having me here today.
Great. Before we get into the design platforms for deflectable endoscopes, based on the growing interest in single-use endoscope platforms, are you seeing interest from medical device OEMs that would like to partner with Biomerics to develop single-use endoscopes?
Absolutely. I've been with Biomerics now for about 4 years, and I've spent about 85% of my time working with various customers interested in launching some type of single-use endoscope device. Related to what you mentioned earlier, usually at a fraction of the cost of reusable scopes, we've been able to develop robust design platforms which have been gaining traction with customers, typically interested in developing one of 4 types. It's either a ureteroscope, which is also called a URF device, cholangioscope or CHF device, bronchoscopes, and colonoscopes.
Okay. Are Biomerics vertically integrated capabilities related to vascular steerable catheters for structural heart and EP therapies transferable to steerable endoscopes?
Absolutely. Actually, the same capabilities that are used to create these types of cardiovascular devices are the same for endoscopes. These would namely be things like extrusion, braiding, reflowing, laser cutting, laser welding. Biomerics, as part of the vertical integration, harnesses almost all of these necessary equipment-related processes that are required to manufacture a steerable catheter. The beauty of our vertical integration is that these processes can be tailored for very custom types of steerable shafts, which are the result of specific customer requirements. And aside from that, too, on the material side, we do stock a wide variety of medical grade polymer resins, which are key in developing both the inner and outer layers of the main steerable catheter shaft.
Okay, great. So the focus of our technical discussion will be related to the flexible shaft of the endoscope, or the steerable endoscope, and that includes the proximal shaft, the distal articulating section, and the components along the length of the shaft. There are other very interesting topics to discuss, such as the handle design, lighting, optics, and imaging, but we'll save that for another podcast.
Sounds good.
Okay. Let's start with the multi-lumen shaft of the endoscope that includes functional lumens for fiber optic bundles for transmitting light at the end of the scope, fiber optic bundles for a camera at the end of the scope, working channels for biopsy forceps and clips and energy devices, auxiliary lumens for irrigation and suction, and then pull wire lumens for tip deflection. That's a lot of lumens.
Yeah.
Do the multi-lumen shafts include a central lumen with auxiliary lumens arranged in a symmetrical pattern or are they arranged in an asymmetrical pattern? And I ask this question because those familiar with the art of complex medical multi-lumen extrusion know that asymmetrical cross sections with uneven wall thicknesses can be quite challenging to extrude due to the polymer flow imbalances.
That's exactly it. It is a challenge in itself. Whenever possible, we try to avoid the multi-lumen extrusion path and actually try to create the lumens during the lamination process. So actually, steerables can be made with multi-lumen extruded tubing, or these lumens can be created during a reflowing or what we call thermal lamination process with the support of wires and custom ground mandrels. In either case, peripheral lumens are typically arranged in a symmetric fashion for the simple reason of balancing the cross-section, which helps in retaining equal flexibility in any direction that you're steering in. However, these are designs which force non-symmetric profiles due to space constraints dictated by the inner and outer diameter of the shaft.
Okay, interesting. Are the materials in a flexible endoscope like the materials used in a vascular steerable catheter with a PTFE inner liner and then outer jacket materials, approximately, nylon 12 as we go down, PBAX and TPU, soft TPU on a tip? Is it similar?
That's basically correct. So you do have the correct sequence of polymer types. Um, However, as you may have heard with supply chain issues surrounding fluoropolymers these days, such as PTFE and FEP, other material alternatives have been adopted as a more readily available lubricious inner liner for the shaft. As for the outer shaft extrusions, both the nylons, PBAX family of polymers are extruded in specific durometers and specific grades. So this allows us to vary the shaft flexibility from the proximal to the distal end. The articulation segment of the steerable catheter, for instance, is not always made of a TPU material or urethane material for that matter. It can also be made of a softer PBAX combined with the correct steel braided mesh, which lies just underneath those outer jackets. So it's a combination of all these materials that create the composite structure.
Okay, great. Walk us through some of the best practices for the coil or braid reinforced proximal shaft of the endoscope that transmits pushability and torque forces to the tip of the endoscope.
Absolutely. So we talk about pushability, torqueability, and flexibility. There are usually three characteristics when designing a flexible endoscope or any braided catheter shaft for that matter. So there are many variations and combinations of internal metal components which strike the balance between pushability, torqueability, and flexibility. Beginning with customer design input requirements, we usually begin the development process by selecting either a braid or coil type of reinforcement. Of course, low-cost options while maintaining performance are also key when designing single-use shafts. Coil designs are typically adopted when superior flexibility becomes one of the most critical performance requirements. On the other hand, braid is the most commonly used component, so you can vary the wire size, the braid pattern, the pick count, and when combined with the outer polymer, normally provides all three characteristics that an end user is looking for. And again, it's a lower cost option. Testing early on in the development phase is necessary when establishing performance criteria, which is often benchmarked against commercially available devices.
Predicates.
Exactly.
Okay, great. Let's move on to the distal articulating section that allows the tip of the endoscope to travel through the tortuous anatomy and to orient the tip of the endoscope in a desired direction.
Yep.
Before we get too deep into the details, please provide a high-level overview of the basic mechanics of what makes a catheter or endoscope steer or deflect.
Exactly. So now we're getting to the business end of the catheter. This is where all the action happens, and of course, most of the cost is put into that articulation segment. You can think of a steerable catheter as a puppet on strings. Like a puppet, the catheter will respond, and it will move in a certain direction depending on which string you pull. Cables or pull wires are typically fixed to the end of the articulation segment, and they're threaded through dedicated channels located in the overall construction of the shaft. The articulation segment of the catheter must always be made of a softer material so that it can easily bend relative to a stiffer material that's just adjacent to it on the proximal side of the articulation segment. The actual mechanical effect which creates the articulation or deflection is caused when a cable or wire, either one can be used in a catheter, is pulled in tension. So this effect causes the softer distal articulation segment to begin compressing against itself as you pull on this cable or pull wire and against the proximal stiffer section of the shaft. When the articulation segment can no longer compress, it begins to bend in the direction in which the cable or the wire is actually being actuated or pulled in.
Okay, thanks for that overview. Walk us through the design platforms for the articulating section. I know there's laser cut hypotubes and molded vertebrae and other types, but if you can give us an explanation of the different platforms.
Sure. So articulation segments come in a variety of different design platforms. Again, these depend on factors like the cost, IDOD constraints of the shaft itself, and the required mechanical strength. Again, these are all user input requirements that we drive off of. The most cost-effective option is the standard braid reinforced articulation segment. So there's no special laser cut or molded components that are required here. You can simply create a single shaft with varying polymer segments and embed the pull wires within the walls of the shaft. So this is what we call a continuous process, where you have a layup that is uniform from the proximal to the distal end, and you would only typically vary the actual durometer segments of that shaft. A more sophisticated design can lead to creating an articulation segment from a laser cut hypotube, a little bit more costly. Typically, this results when very controlled planarity is required, as well as a shape variation during articulation. We see this a lot in the endoscopes. So a typical braided catheter with a braided articulation segment that doesn't have any special laser cut components will usually articulate in a circular arc. Well, normally for your ureteroscope or cholangioscope type applications, we're going to need that device to articulate maybe in a D shape or a P shape fashion. So that's when these specialized components come into play. A lower cost option to the laser cut metallic articulation segment is the molded backbone or vertebra or vertebrae. It's another attractive option where you can also mold the control cable lumens directly into the walls of the vertebra itself, and it doesn't interfere with the ID of the catheter. So several options are at play, and again, it all depends on cost and end user requirements. But we always try and keep things as simple as possible and keep the platforms as simple as possible.
Okay, great. Earlier, when you were explaining the mechanics of steerability, you mentioned different wires that can be used. So the pull wires extend from the handle of the endoscope and are attached to a pull ring near the distal end of the device for bidirectional or four-way tip deflection. What are the different options used for steering tethers that are used for steerable or deflectable endoscopes?
There's really only two types that are conventionally used today as far as metallic tethers are concerned. We can get into this if we have a little bit more time in this podcast, but we also use polymer types of tethers as well in situations where the catheter is designed in an MRI application where you can not have any metallic components on the inside. One of the classic examples of non-metallic tethers is using a material called Kevlar, which is the same material used in bulletproof vests. But aside from that, stranded cables and solid wires are the most commonly used tethers. The stranded cables are attractive when you need more flexibility in bending. So as you're steering the catheter, they don't resist articulation as much as a solid wire would. On the other hand, solid wires have higher tensile strength and they also have lower surface friction. Flat wires are essentially the same as a round wire, but used in situations where you have very limited available space within the shaft walls. So instead of having a round wire, you would go with something that perhaps has the same cross-sectional area and is flat so that it fits a little bit easier into these constrained spaces.
Lower profile.
Exactly, lower profile options.
You mentioned an MRI, and that's something that I haven't heard of in a while. At one point, a few years ago or more, there was a lot of talk about MRI compatibility and
Yep.
folks were coming out with different reinforcement materials, LCP and PEEK.
Yep.
And I thought that kind of went away because I didn't see a lot of that. But any updates on that MRI compatibility?
It's obviously the market is not calling for as much of that right now as opposed to the traditional single-use endoscopes that uses the traditional polymer metal layup. But there are some companies that do look for MRI compatible platforms, whether it be in standard sheathing or whether it be in steerable cardiovascular type sheaths. And so it does drive a new challenge where we have to completely think outside the box in terms of how we're going to braid the shaft, what kind of pull wires we're going to use, and everything, of course, is converted to a non-metallic construction. So there are, like you mentioned, there are available materials that are commonly used like Kevlar, PEEK, Vectran is another one. It's a trade name for essentially glass fibers. And we can also process these on our machines that we would normally use for their metallic counterparts.
Okay, and thanks for that update. What can you share about joining the proximal insertion tube to the distal articulating section for a smooth transition of the working channels and other functional lumens?
This is key. Some platforms don't require any joining at all, but it can be done in two ways. Some steerables don't need to have separate joints between these two segments, the proximal shaft and the distal articulation segment, since the entire shaft, including the articulation segment, can be made in a single process, as I mentioned earlier in the podcast. This is what we call a continuous reflowed shaft. But shafts that do require joining the insertion tube or the proximal shaft to the articulation segment typically result in some sort of a laser welded joint, a solder joint, an adhesive bonded joint. The joining process itself can't be made without some sort of receptacle built into the insertion tube that would be capable of mating and accepting the articulation segment itself. So there are some conventional ways of doing it, but again, depending on the user and needs and the design that is usually driven by the customer, we can accommodate and we can vary the way this is done.
Okay, thanks. Alan, this has been a great discussion. Thank you so much for joining the MEDX podcast today.
It's been a pleasure, Steve, and I hope to be back again soon. Thank you.
Thank you for listening to MEDX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. All links are available in the show notes.